Hello everyone, my name is Nandkishore Yadav from ABES Engineering College, Ghaziabad. Today I am going to discuss recursion and its important application, which is known as a Tower of Hanoi problem. Firstly, let me introduce what is a recursion. So recursion is basically a programming technique where a function call itself. Generally, a factorial program is used to see an example of recursion. So we have already seen how a factorial is calculated using loops. So here we are not using loops. We are just going to calculate a factorial using recursive. In the first step, let's see how to write the algorithm for recursion here. So here, let's write, see that int fact int n. If n is equal to 0, return 1. Else return n into fact and minus. Okay. So suppose we want to calculate the factorial of a number that is called n is equal to. So for n is equal to 3, let's see how do we calculate the recursion. So here we put fact n is 3, so n is equal to 3 here. Then what do you write? Then in next step, again this function put the value 3 in this recursive function. From here, for the value of n is equal to 3, it will not call the base condition. It's called the base condition in recursive function. It's basically a stopping condition. Okay, so this is called base condition. Every recursive function has a base condition by which it can after meeting this base condition, a factorial can stop itself. Okay. Recursive function can stop itself. So here base condition is not matched, then we have for n is equal to 3, we put value of 3 here, and in next step again we calculate fact for n is equal to, because here n is equal to n minus 1. Put value of n3, then it's come 2. And next step we calculate 2 into fact 1. When again this function call itself, it will return 2 into fact n minus 1. And after all, in last step, it will calculate fact 0. As we know, for n is equal to 0, the base condition will works and it will give the value 1. And this 1 returns to this this function 2 into 1. Here we have calculated 2 into 1. Again, this value returned to this one. Okay. Here we have calculated 3 into 2. Both values. It got is received a value after calculation. Now, this is the way we can calculate a factorial for 3. Generally, there are two types of recursion we can see. One is called tail recursion, another one is called head recursion. The tail recursion, a recursive call, is at the last operation that is performed in the function. After this call, nothing we have to do. We can't do any operation, like we can't add two things or subtract two things, or we can't make print operation over there. There is an example of tail recursion is that suppose we are having a function called void print int n. If we say write base condition like if n is less than 0, then function should return else, or we can write here print %d %n or print and -1. So here we have calculated this recursive call at the last line. After that, we doesn't have any print operation or any arithmetic operation after this function. So this is the tail instruction we can. So here, if this type of approach is followed, then over there we can see there is a tail recursion. Similarly, when what how we can see head recursion? In head recursion, the recursive call occurs before any operation in the function. So for head recursion, what will be the program? Suppose we are having again void print for int n. If we write base condition like if n is less than 0, तो return कर जाए, return, else we can write here we have called print n minus 1 before print statement. Printf, this is the printf, not print. So printf %d. So here we have write this statement after the recursive call. So this is called the head recursion. Okay. So in the head recursion, recursive call is before this statement. It's called the head recursion. Now there are so many applications of recursion in data structure. While we solve the problems of uh, traversing, we can apply the recursion in traversing of binary trees, where we can see a recursive function for pre-order traversal, in-order traversal, and post-order traversal. Similarly, while we dealing with the binary search tree or a graph, like a graph, then over there we can also meet these algorithms recursively. Secondly, we can see recursive approach in merge sort, quick sort, and binary search also. Various mathematical problems like factorial, Fibonacci, greatest common divisor, that's called GCD. Over there, we can solve these problems by recursion. Now, let's see an important application of recursion that is called Tower of Hanoi problem. So let's firstly let me introduce what is Tower of Tower of Hanoi problem is. So Tower of Hanoi problem is a puzzle where it involving three rods in this puzzle, and there are number of some disks. Okay. Now the puzzle start with all the disk of stack in one rod in descending order, with the largest disk at bottom. Suppose we are having a rod like this. In this rod, we are having three disks. So it is the largest disk. It is the second largest. It is the smallest disk. So after that, we can also have another disk, fourth one. So it is the smallest disk. So in this arrangement, we are having n is equal to 4. So here total disks are 4. So this is the smallest disk and this is the largest. So the problem start with any number of disks, but there are fixed number of rods. There are three rods. So how we can represent this problem? We can see in this problem we are having three rods. Suppose this is rod A, another rod B, and C. Okay. So this rod A is we can assume as a source rod, and rod B we can assume as a destination rod. Sorry, auxiliary rod. And rod C we can assume as a destination rod. So in this problem, we have to move this arrangement of four disks to destination rod. So exactly in the Tower of Hanoi problem, we will see how do we can transfer all the disks to destination rod. Before moving this, let's see what are the rules to transfer the rods. So there are basically three rules, basically two rules. So all the disk we can put in this arrangement is increasing order. It means that the smallest rod is always at top, or smaller rod is always at top. A greater rod will be at below that. Okay. And second is rule is that uh, we have to move only one disk at a time. So these are two rules we have to follow in the case of tower of any problem. So using these rules, following these rules, we can see the applications of tower. How do we solve the this problem using recursion? So problem says that if you are having three disks, like this one, suppose we are having three disks here, disk one, disk two, disk three, three, two, one, and this is our rod A, this is our rod B, and this is C. So here we are having three rods. We have to move this arrangement to rod C. Okay, and rule is that we can only move only one disk at a time. Firstly, what we do, we we have to move n minus one disk from source rod A to auxiliary rod B. So here we are using intermediate rod this B. So first step, what we do, we just move uh, keep rod 3 at same place and move this arrangement at this position. So here disk 2 and disk 1 we have moved at position B and at rod B, and rod C is vacant. In third step, what do we do? We can move rod third disk, keeping it same. So now third disk as rod 3. At last step, what we do? We can move this arrangement up to rod. So rod B is vacant now. And what about rod C? Rod C, when we move this arrangement, whole arrangement to this one, so this is called final. Uh, Finally, we have transfer all the disk to rod C using this approach. So how do we write the recursive solution for this algorithm? So in the first step, we write void tower A, B, C. So A, B, C are the three rods here. What is the base condition? If n is equal to, okay, we are writing here n. If n is equal to 1, so if there is only one disk, then what we do? We can simply move disk from disk A to disk C. So we have to print move A to C1. Else, what do we do? Else, or we can write here, uh, then if it is not equal to 1, then only call tower, or we what we do, we can move disk, we can move these two disks to uh, arrangement B. What we write, we can move A as a source, B as a destination, and C as a auxiliary dot for n minus. Similarly, and the next step, what do we do? We have moved these two disks to rod B using C. Okay, and in second step, we'll write print print. Now we can see that there is a rod, a third rod is at place A. Then we can also move this rod to C. Then we can move and print A to C. Last, we can see only two n minus one disk are at position B, then we can, in the third step, we can move all n minus 1 disk to disk C using A as an auxiliary disk. So here we can write tower. B is our source. B is source node for this arrangement. C is destination, and we are using E as an auxiliary for n minus 1. So here we can give a recursive solution to tower of Hanoi problem in this way. So now let's see what are the various applications of tower of Hanoi problem. So there are, we can see there are recursive call. There are tower of Hanoi problem is used for demonstrating the stick-like behavior for recursive call. Simulation scenarios involving source, reallocation, and a recursion-based solution. Studies as a model for the cognitive problem solving and memory. Okay. Thank you.